In this lecture, we want to talk about hypothesis testing for a mean. Okay, so for some population mean, and this is when sigma, the population standard deviation, is unknown. So in a previous lecture, what we did was we did the hypothesis testing for a mean when you knew sigma, when you knew the population standard deviation. So for this lecture, we're going to say, okay, this is a more realistic um, type of procedure for hypothesis testing. When you don't know the population standard deviation, how can you perform a hypothesis test? Okay, but you're going to need two things for this lecture. You're going to need the t-table, the student's t-table. This is attached to this lecture, so have this handy. And then you'll also need your graphing calculator for this lecture. Okay, so what's going on in this case? So to test a hypothesis regarding a population mean, assuming the population standard deviation of known, we're going to need to use the t-distribution, okay, rather than the z-distribution. This is because when you don't know sigma, okay, when sigma is unknown, you estimate it with S, okay, the sample standard deviation. All right, and what we learned was, and when we were talking about this under the confidence interval lectures, whenever you're going to do this calculation here, okay, x bar minus mu divided by S divided by the square root of n. Okay, so previously our test statistic previously was this x bar minus mu sub 0 divided by sigma over the square root of n. Okay, this followed a normal distribution. Okay, but when you replace sigma with S here, okay, this follows a t-distribution. Okay, so this follows a student's t-distribution with, this is what we call this df, degrees of freedom, n minus 1, so the sample size minus 1. And we use this degrees of freedom to look up critical values on the t-table. And we're going to do this 3 times. I have 3 examples of this, so don't stress if it's kind of slipped your mind how you've done this. Don't stress. I've got 3 examples where it'll come back. Okay. So when you're going to do testing a hypothesis regarding a population, okay, we use the following steps that I'm going to have. So the following steps I'm going to show you is those 5-step process. Okay, provided that you have the following. All right, one, that the sampling method that you do is obtained using simple random sampling. Okay, so for our class, we'll assume this to be true. This one here, okay, the sample has no outliers, okay, and the population from which the sample is drawn is either normally distributed or has a sample size that is large, which is greater than or equal to 30. This comes from the central limit theorem. And in all the problems that we do or that I give you, if the sample size is less than 30, we will assume it's normally distributed. And 3, the values or the sampled values are all independent of each other. So we'll just assume that all these check out for our class, okay? So we'll assume these are all met. So in the real world, when you leave college and you have to go do statistics on your own, you'll make sure to verify these on your own. But for now, I just want to get through the 5-step process for hypothesis testing, and we'll assume that these are all met. Okay, so basically from the previous lecture, okay, the 5 steps are the same. Okay, just some of the notations. Okay, so step 1 had 2 parts. We're going to define the parameter. So in this case here, it's always going to be like let mu equal, and then what mean we're talking about. And then you're going to set up your test. Okay, so again, you're going to have a left-tailed test, a right-tailed test, or you can have a two-tailed test. So, it's mu is equal to something and we want to test. Wait a second, no way, no way. Mu is less than that number. Right-tailed test, mu is equal to a number, the mean, and we're saying, no way, the mean is greater or the mean is increased. It's no longer that number, it's gone up. And then you have a two-tailed test where you say the null is mu is equal to something number, and the alternative is no way, it's not equal to that. It's changed, it's different. Okay, so after we do that, step 2 is you're going to select your level of significance. So for our class, this will always be given. It'll be alpha, and the 3 common ones are 1%, 5%, or 10% level of significance. Okay, you're going to compute the test statistic now. Okay, and in the previous slides, in the previous lecture, it was denoted as t sub 0, or excuse me, it was denoted as z sub 0. Here it's denoted as t sub 0. And what you do is you take the sample mean minus mu naught, which is the assumed population mean, divided by s divided by the square root of n. So s is the sample standard deviation, and n is the sample size. So just so we're clear again, x bar is the sample mean. Mu sub 0 is the assumed population mean. It comes from the null. S is the sample standard deviation. And n is the sample size. Okay, so the next thing you have to do is you have to find the critical values or critical regions. Now, this is a little bit more difficult than in the previous lecture. So in the previous lecture, I gave you a nice cheat sheet of the critical values. For this one here, you're going to have to, every single test, you're going to have to look them up on this T table here. Okay, there's no easy way around it, unfortunately. You're always going to have to look it up. Okay, and I will explain in the coming slides how you find the critical values and critical values. And then step 5, you have your conclusion. And so you can either reject the null or you can fail to reject. So if the test statistic is in the critical region, okay, when you draw your t distribution, you're going to reject the null hypothesis. If the test statistic is not in the critical region, okay, you're going to fail to reject the null hypothesis. Okay, and I'll have 3 examples of this for you. Okay, so what's really difficult perhaps about in this section is, how do you find the critical values? Okay. So to find the critical values, you're going to use this t table that I said, and you're going to need 2 things. Okay, you're going to need df, which is the degrees of freedom, okay, which is n minus 1, and you're going to need the upper tail probability, which I'm going to call UTP. Okay, for a right-tailed or left-tailed test, the upper tail probability is just your level of significance alpha. Okay, if it's a two-tailed test, your upper tail probability is actually alpha divided by 2. So you split your level of significance, your alpha in half, because you could change your two-tailed test by being greater than or less than. You need to cover both cases. So let me show you now what the critical regions and critical values will look like when we sketch them. So for a two-tailed test, what you'll do is you'll draw a t distribution, which we know looks like a normal curve. Okay, and it's going to be centered at the number 0. And then you're going to look up the critical value on the table. And don't worry, I'm going to walk you through 3 examples of this. And when you go to the t table only gives positive numbers. It actually only gives the upper t critical value. So if you need to ever find a negative one, you just look up the positive and put a negative number on it. So two-tailed tests will have 2 critical values. A right-tailed test, and the critical regions you're going to shade, to the above your critical value and below your critical value here. A right-tailed test has 1 critical value, this t of alpha, and you're going to shade everything to the right of it, and that's going to be your critical region. So remember, the critical region is the rejection region. And again, this is centered at 0. Left-tailed test has 1 critical value minus t of alpha, okay? And the critical region you're going to shade to the left of it. All right, I know it can seem confusing the first time, but I promise you after you see an example or two, I'm going to work three. It's going to be, I think it'll make a lot of sense. Okay, so I'm actually going to work the hardest problem first, and then I'm going to have two easier ones to follow. Okay, so this one is about acid rain, example. So acid rain from the burning of fossil fuels has caused many of the lakes around the world to become acidic. Okay, so the biology in this lake often collapses because of the rapid and unfavorable changes in water chemistry. Ooh. So a lake is classified as non-acidic. So it's classified as non-acidic. Okay, if its pH the pH level is greater, if it has a pH level greater than 6. Okay, so these two authors here measured the pH of high mountain lakes in the Southern Alps and reported their findings in this paper. Okay, and the table below shows the pH levels obtained by the researchers. Okay, so these are, it looks like they have one, two, three, four, five, looks like they have 15 lakes that they sampled. Okay, and so here's what we're asking. At the 0.05 level of significance, okay, determine whether the data provided sufficient evidence to conclude that on average, high mountain lakes in the Southern Alps are non-acidic. Okay, so remember, a lake is classified as non-acidic if its pH is greater than 6. Okay, so we want to conduct a hypothesis test to see if these lakes, okay, on average, right, are non-acidic. Okay, so we want to test to see if their pH level is greater than 6 on average. Okay, first thing you'll notice here in this problem, going back real quick, what you need is you need to know the sample mean, the sample standard deviation, and the sample size. Well, good news is we have the sample size. We need to find the sample mean and sample standard deviation pH levels from these lakes. All right, so it's not directly given to you, but you can actually use your graphing calculator here to find it. Okay, so what we're going to do is we're going to take our data, okay, and plug it into our calculator. So to do this, recall, you're going to hit the stat button. And under number one, okay, you're going to edit the list. Edit and then edit the list one. And so hopefully what you want to see up here is L1. If you don't see L1 up here, you should reset your calculator. Now what you want to do is you want to start inputting all these 15 values. Okay, so I'm just going to minimize this real quick on the lecture so I can see all the values, and then I'll expand it back up. So it's 7.2, and I'm going to go down all the rows. 7.3, 5.7, 7.3, 6.3, 6.9, and over here 6.1, 5.5, 6.7, 6.9, 6.3, 7.9, 6.6, 6.5, and then 5.8. Okay, so now I have all the data correctly plugged in. So the next thing I'm going to do is I'm going to have my calculator compute the sample mean and sample standard deviation for us. So what I'm going to do is I'm going to hit the stat button. I'm going to go over to calc, and I want 1-var stats. Hit enter. It is under list 1. Now if you have a TI-83, just hit enter again. Okay, TI-84, you got to go down to calculate. You should see this. Okay, so right off the bat, X bar is 6.6. And S, the sample standard deviation, going back, I'm going to go out 4 decimal places here, is 0.6719. Okay, great. So now what we got to do, right, now that we have that, just some other things that are given, we got the sample size is given as 15 and alpha is 0.05. Okay, now what we can do is we can go through the hypothesis testing. Okay, so first off, step one, define the parameter. What exactly are we investigating here? Well, what we're investigating here is the mean pH level of high mountain lakes in the Southern Alps. So we're going to let mu equal the mean pH level in high mountain lakes in Southern Alps. Okay. And what we want to do is we want to test to see that their pH level is greater than 6 on average. So right there, this right here tells me that it's going to be a right tail test. So it's going to be mu is equal to a number, and it's going to be mu is greater than a number. And what we wanted to do was we wanted to test to see that on average is greater than 6. Okay, so if we're going to test to see if on average is greater than 6, we'll start with the assumption that it is 6. Okay, so just remember when you do hypothesis testing, these two numbers need to be the same. So if you start with the null, or excuse me, you start with the alternative that mu is greater than 6, you'll know then that just like, okay, my null has to be the assumption that it is 6. So the level of significance was given as 0.05. Okay, now let's go through and compute the test statistic. X bar was that 6.6 minus mu sub 0. That comes from the null up here, minus 6, divided by S, which was 0.6719 when I rounded it, divided by the square root of 15. All right, so you're going to grab your trusty calculator here. And then in parentheses, I'm going to put 6.6 minus 6, close the parentheses, divided by, start a new set of parentheses, 0.6719 divided by the square root of 15. And this should be my test statistic, 3.459 when I round to 3 decimal places. Okay, so now I need to compare this number to the critical values. So to do this, what you're going to do is you're going to draw a t-distribution. Okay? And it's centered at 0. And my critical value is t of alpha. And I'm going to shade everything to the right of that. Okay, so how do you find t of alpha? Well, first off, degrees of freedom are n minus 1. Okay, so that's 15 minus 1, which is 14. And the upper tail probability. Well, whenever you have a right-tailed test, the upper tail probability is just alpha, which is 0.05. So here's what you do. You grab your table. Upper tail probability is 0.05. Degrees of freedom, whoop, go down to 14. You go over to where the row and the column intersect. You get the number 1.761. So that's my critical value, and everything past that is the critical region. Well, here's 0. Here's 1.761. This number here is way over here. So it's in the critical region. It's in the critical region. So what do? We reject the null hypothesis. And this is because our test statistic is in the critical region. Okay, so what that means is evidence suggests the mean pH level is greater than 6. Or that these lakes are non-acidic on average, is what this is also testing to see. So there you go. So generally I think the hardest part is setting up the test, because once you set up the test, like the rest of this is just a calculation, and this is just a number comparison. Once you set this up, it kind of just falls into place the rest of it. All right, let's do 2 more examples. So according to the most recent General Social Survey, so I've done, this has come up before, This is a survey of opinions and lifestyles of U.S. adults, and this is conducted by the National Opinion Research Center, NORC, at the University of Chicago. And this is from 2017, okay? So this is the most recent one I have data from for this. Okay? The average person, just so the average adult, watched 238 minutes of TV per day. Okay, all right, that's a lot, that's quite a bit, almost 4 hours a day, okay. So a researcher believes that the mean hours of TV watched now by millennials, okay, so by this by the millennial generation, right, is different from this amount, okay. So if this researcher thinks it's different, that's a keyword that tells me this is going to be a two-tailed test. Okay, so to test this claim, the researcher samples, so 51 millennials, so you're given X bar, and finds that they watch 215 minutes on average. Okay, so the average amount of TV they watch per day is 215 minutes. With the standard deviation, S, sample standard deviation of 115 minutes. Okay, so at the 0.01 level of significance, so alpha 0.01, is there evidence to suggest, sorry, a little bit of a typo there, that millennials do not watch TV at the same level, okay, so that it's different on average as the average person in 2017. Okay, so when I say they do not watch it at the same level, this means that it's different. Okay, so that on average they're watching a different amount of TV. The researchers like maybe it's gone up, or maybe it's more than 238 minutes on average, maybe it's less than. I'm not sure. All right, so you've got the 4 key numbers you need to answer this. Let's go through and do the hypothesis testing. Okay, so step 1, define the parameter. So what we're investigating here, we're going to let mu be the mean time millennials, okay, spend watching TV per day. And we want to test to see if it's different from that 2017 level. Okay, so it's mu is equal to a number versus mu is not equal to a number. And what we're testing to see that it's different from, okay, is that it's different from the 238 minutes on average. All right, so select the level of significance. I'm going to give you that. It's 0.01. All right, let's compute the test statistic now. Okay, so it's X bar, the 215 minutes, minus mu naught, which is 238, okay, because that's what we're testing to see that it's different from. The standard deviation was 115, and the sample size was 51. All right, so again, grab your calculator. So it's 215 minus 238 divided by 115 divided by the square root of 51. And our test statistic comes up to be negative 1.428, negative 1.428. Okay. So now you've got to compare this number to the critical value critical region. So you're going to draw a t distribution. A little sloppy there, I'm sorry. Centered at 0. And so it's a two-tailed test. So it has 2 critical values. T of alpha divided by 2. And you're going to shade to the right. That's one critical region. And then another one was negative T of alpha divided by 2. And you're going to shade to the left. Okay? So what is T of alpha divided by 2 equal to? Well, first off, you need degrees of freedom. That's n minus 1. So that's 51 minus 1, that's 50. And the upper tail probability for a two-tailed test is alpha divided by 2. So you've got to take this alpha. Only for a two-tailed test do you do this and divide it by 2. and you get 0.05. So now grab your t table. Upper tail probability, go over to 0.005. Be careful that you don't go to 0.05. Okay, it's 0.005. And then you're going to scroll down to 50, which is over here. And so 0.005 and 50 cross at 2.678. 2.678. Okay, so that means one critical value here is 2.678, and the other one is minus 2.678. Okay, so whenever you need to look up a negative one, just look up the positive and whoop, put a negative one. So now ask yourself this, does my test statistic go past this number down here? No, it's kind of like right here, right? Right, negative 1.428 is between 0 and negative 2.678. So it's not in a critical region. So we fail to reject the mean. And this is because our test statistic is not in a critical region. And so what's going on here is evidence does not suggest the mean, okay, hours of TV watched per day by millennials is different from 238 minutes. So right now, there's no reason to suggest that millennials watch any different amount of TV on average than an average person. Okay. So we've done one case where you reject, right? So when the test statistic is in the critical region, you reject. And then when the test statistic is not in a critical region, you fail to reject. All right, let's do one last one. So we've done a right tail, the two-tailed. Let's maybe do a left tail. Okay, so this one's about good credit. So the Fair Isaac Corporation, FICO, or a credit score, is used by banks and other lenders to determine whether someone is a good credit risk. So scores on your FICO score range from the lowest it can be is 300 and the highest it can be is 850. So with a score of 720 or more, indicating that a person is a very good credit risk. So if you have a credit score of 720 or more, you're good. So an economist wants to determine whether the mean FICO score is lower. So the average FICO score is lower. So that tells me it's going to be a left-tailed test. And the cutoff of 720. Okay, so this economist, she finds that that a random sample of 100 people, so you're given n, had a mean FICO score, so their X bar was 703 with a standard deviation of 92. Okay, can the economist conclude that the mean FICO score is less than 720 and use the 0.05 level of significance? Okay, so I'm not sure, right? So even though we talked to 100 people, the mean was 703. That's for sure less than 720, but that's not exactly how statistics works. You just can't say, oh, it's less than, so I can for sure say the value is less, the average is less than 720. It doesn't work like that. This is just a random sample of 100 people. Again, we need to test to see if it's statistically significant, this value of 703. Okay, so what we want to test to see is if the mean score is less than 720. Okay. So again, what parameter are we looking at? We're looking at let mu equal the mean FICO score. And what we want to test is to see if the mean is less than 720 on average. So to do that, our null assumption will be, yeah, we'll just assume it is 720. Level of significance is 0.05. We got that. Compute the test statistic. Well, the average was 703 minus 720 from the null. S was 92. The economist, she talked to 100 people. 92 divided by the square root of 100. So grab your calculator. 703 minus 720 divided by, another set of parentheses, 92 divided by the square root of 100. And you get minus 1.848 when I round it. Okay, so critical regions, okay? Critical values. So you're going to draw a t-distribution. Centered at 0, okay? And my critical value is minus t of alpha, and it's a left-tailed test, so I'm going to shade to the left. All right, so minus t of alpha, what is this equal to? Well, you need degrees of freedom. It's 100 minus 1, which is 99. You need the upper tail probability. Since it's a left-tailed test, it's just alpha, 0.05. So here's 0.05. And you'll notice next is when you go down the chart, there is no 99. Okay. So when that happens, what you do is you use the closest value, which is 100. Okay. So 100. So you go over from 100 and you go down from 0.05 and you get the value of 1.660. Okay, so if you're looking for the negative, it's just negative 1.660. Okay, so look, is our test statistic? Yes, it is past this, just barely. It's it's real close, but it is in the critical region. It is. All right, it's just barely past this. So what we do is we reject the null. All right, and this is because our test statistic test statistic is in the critical region. So unfortunately, what that means is that there is evidence does suggest the mean FICO score is below 720. So on average, Americans don't have very good credit. Which is unfortunate that this is what this test said. Okay, class, so I've done 3 examples, a left-tailed, right-tailed, and a two-tailed. Here's two-tailed, and here's the right-tailed. If you have any questions, let me know.